In this video, I will be discussing an important type of elimination reaction, pyrolytic syn elimination reaction. Pyrolytic syn elimination reaction. This reaction is otherwise called EI elimination because it takes place by internal mechanism. The eliminating groups, the leaving group and the proton from the beta carbon atom are syn periplanar in orientation, and hence it is called syn elimination reaction. Syn elimination reaction. You can see the leaving group and the proton in the beta carbon atom are oriented in syn periplanar conformation, and hence it is called pyrolytic syn elimination reaction. Pyrolytic syn elimination reaction. It is taking place by high temperature and it does not involve any acid or base catalyst and occur in gas phase. Also, it is a concerted mechanism or one-step reaction with the involvement of a cyclic transition state. Usually, it is a regioselective reaction and Hoffman product is obtained as the major product. These are some of the important features of pyrolytic syn elimination reaction. Okay, some of the important pyrolytic syn elimination reactions are pyrolysis of acetate, pyrolysis of xanthate ester, or Chugaev elimination reaction, and pyrolysis of amine oxide. Otherwise, it is called Cope elimination reaction. Okay, let us first discuss the pyrolysis of acetate. In pyrolysis of acetate, an acetic acid molecule is always eliminated with the formation of an alkene. You can see the propyl acetate upon strong heating, it eliminates a molecule of acetic acid forming an alkene, propene. If you examine the mechanism of pyrolysis of acetate, you can see the leaving group, acetate group, and the proton in the beta carbon atom are oriented in the same direction, or they are syn periplanar to each other. A proton from the beta carbon atom is captured by this oxygen, carbonyl oxygen, forming a cyclic transition state first, which decomposes to form propene and acetic acid. It is a one-step concerted reaction. It is one of the important feature of pyrolytic syn elimination reaction. That is, pyrolytic syn elimination reaction proceeds via a concerted mechanism, or it proceeds in a single step with the formation of a cyclic transition, right? One of the important feature of pyrolytic syn elimination reaction is it is regioselective. See in this example, 2-isopropyl 2-methyl ethyl acetate. When it is heated, we get this Hoffman product as the major product. See in this example, that is 2-isopropyl 2-methyl ethyl acetate. You can see there are 3 beta carbon atom on either side of the acetate group, the leaving group. It is beta carbon atom, and hence there is a beta hydrogen atom which is already oriented in syn periplanar directions. If the CO group, the oxygen atom of the carbonyl group, capture this proton, we will get a sides of product, more substituted product. But it is less accessible because the steric crowding of these two methyl group impede the capture of proton from this beta carbon atom. But if we examine this beta carbon atom and this beta hydrogen atom, this carbonyl oxygen can capture easily this proton from this beta carbon atom, and hence we get this Hoffman product as the major product. Thus we can say the pyrolytic syn elimination reaction is regioselective, and hence carbonyl oxygen capture a beta proton from easily accessible beta carbon atom. Okay. Another example of pyrolytic syn elimination is elimination of acetate from this molecule by heating this molecule into 450 degrees centigrade. You can see there are 2 beta carbon atom in this molecule, this beta carbon atom and this beta carbon atom. So there are beta hydrogen atom here and here also, but the beta hydrogen at this position is easily accessible for this carbonyl oxygen to capture, and so usually a Hoffman product is obtained as the major product. About 65% of 1-butene is produced as the major product. But you can see here also a beta carbon atom, and this beta hydrogen atom, which is if the carbonyl oxygen is captured this beta hydrogen atom, then we'll get the sites of product, more substituted product, which but obtained as the minor product because the capture of proton from this beta carbon atom is impeded by this methyl group. The steric hindrance impeded this oxygen atom to capture from capturing this proton atom, proton, and thereby we'll get the sites of product as the less substituted product. So we can say the pyrolytic syn elimination is regioselective. The capturing of proton by the carbonyl oxygen is usually taking place from less hindered region. That is why we'll get the Hoffman product as the major product in pyrolytic syn elimination reaction. Another important pyrolytic syn elimination reaction is Chugaev elimination reaction. In Chugaev elimination reaction, a xanthate ester, it is a xanthate ester, upon heating we get corresponding alkene, Hoffman product as the major product, as in the previous case. Here the eliminating groups are xanthate ester group and the proton from the beta carbon atom. Here this xanthate group and the proton from this beta carbon atom are on the syn periplanar conformations. These are in syn periplanar conformation, and hence these xanthate groups and this beta proton are eliminated, forming this product. But this is obtained as the minor product. It is a sites product or more substituted product because this sulfur, the capture of proton from this carbon atom, beta carbon atom, by this sulfur of the xanthate group is impeded by the steric hindrance of this bulky methyl group, and so it is less accessible. But here also a beta carbon atom, and so there are two beta hydrogen atom. One of the beta hydrogen atom is on the same side of this xanthate ester group, and this sulfur capture this easily accessible proton from this beta carbon atom, forming this alkene, which is obtained as the major product. And so here also this reaction indicates that Chugaev reaction is regioselective, and hence the Hoffman product is, or the less substituted alkene is obtained as the major product. This is another example of Chugaev reaction. You can see this hydrogen atom is in the beta carbon atom, is in the opposite side of the, or anti to this xanthate ester, and hence there is no double bond formation between these two carbon atom. But here is a beta carbon atom. One of the hydrogen atom will be in the same side of the xanthate ester, and hence that proton is captured by this sulfur atom, forming a double bond between this carbon atom. And so this product will be obtained from the from this reactant by Chugaev's elimination reaction. Okay, another important example of pyrolytic syn elimination reaction is pyrolysis of amine oxide, which is otherwise called the Cope elimination reaction. Cope elimination reaction. In a Cope elimination reaction, a tertiary amine oxide, for example this compound, which on heating, strong heating, we get an alkene, a Hoffman product as the major product. This alkene is obtained as the product by the Cope elimination reaction of this tertiary amine oxide. You can see this tertiary amine oxide in turn is formed from the tertiary amine, by the oxidation of this tertiary amine with hydrogen peroxide. The tertiary amine oxide, upon strong heating, we will get this Hoffman alkene, Hoffman product. That is, it is regioselective. The Cope elimination reaction is also regioselective. It is an example of pyrolytic syn elimination reaction. This is another important example of Cope elimination reaction. Here you can see there are two beta carbon atom on either side of this eliminating group or the leaving group, tertiary amine oxide. This proton and this proton, I mean this hydrogen and this hydrogen, are on the same side of this leaving group, tertiary amine oxide, and hence this oxygen may capture this proton from this side or from this side. If oxygen capture this proton, we will get this product. It is less hindered proton. It is less hindered proton. You know, the Cope elimination reaction is regioselective, and hence we get the Hoffman product as the major product. It is 100% Hoffman product. 100% of Hoffman product is obtained because the capture of this proton from this beta carbon atom is impeded by this isopropyl, a very large group, and thus there is no possibility for capturing this proton from the beta carbon atom here, and so there is no possibility for the formation of any amount of shades of product or more substituted alkene. So 100% of this alkene, the Hoffman alkene, that is less substituted alkene, is produced by this molecule by Cope elimination reaction, right? In this example of Cope elimination reaction, you can see this tertiary amine oxide. Upon Cope elimination reaction, we get 97% of this product, the Hoffman product, less substituted alkene. You can see it is the beta carbon atom. Here also there is a beta carbon atom, but this hydrogen from this beta carbon atom is in the less hindered state, and hence this oxygen capture this proton, forming the less substituted alkene or Hoffman product as the major product. About 97% of this Hoffman product is formed from this tertiary amine oxide. As in the previous case, this tertiary amine oxide is obtained by the oxidation of this tertiary amine either by hydrogen peroxide or peroxyacetic acid. Okay, it is another important example of Cope elimination reaction.